last time we have discussed about some named photoreaction. We have started named photoreaction, in which the first two reactions which we have discussed last time is photophrase rearrangement and Barton reaction. We mentioned that when we have the aryl ester or aryl amides under photolytic condition undergo alpha bond cleavage, and then these giving rise to acyl radical and alkoxy phenoxy radical, and these two once again react to give you ortho acyl phenol or paraphenyl phenol, or if we have we start with the ester, and if we start with the amide, we get ortho acyl amine or para acyl amine. So this was regarding photophrase rearrangement. As far as Barton reaction is concerned, the nitriles also under photolytic condition undergo homolytic cleavage, giving rise to nitroso radical as well as the hydroxyl, what we call it as a alkoxy radical. And then this so this Barton reaction involves four different steps: homolytic cleavage to give of a nitrile to give nitroso, and then the oxygen radical which is generated during the homolytic freeze abstract hydrogen atom abstraction from the adjacent methyl group, and then the to generate CH2 radical, which combined with nitroxyl radical to give this nitroso derivative, which tautomerizes to give oxime. So this is what we have discussed last time, and today we would like to study the photochemistry of some related system, and it has been reported that aryl halides, especially aryl bromides and aryl halides. So aryl bromide and aryl iodides are known to undergo photo-induced homolytic alpha bond cleavage, so and giving rise to halogen atom and aryl radical. And these aryl radical produced have been used successfully in a number of synthetic sequences. So there are very interesting reactions where aryl halides, which involves mainly the aryl bromide or aryl iodide, under photolytic condition undergo alpha bond cleavage to give halogen atom X dot, halogen atom radical and aryl radical AR radical, and then these aryl radicals are known to undergo to synthesize very interesting synthetically important compounds, which was difficult to synthesize through any other catalytic method. So a few examples are reported here. Here in example, here you can see this is a aryl iodide. This is aryl iodide connected to the benzene ring, and then this is through a alkene double bond. You have another moiety here, and then so you can see it is two aryl groups are separated by a methylene group in a cis, or it can undergo cis trans isomerization as well. So under photolytic condition, it undergoes homolytic cleavage. The cleavage, homolytic cleavage, homolysis, to give aryl I dot as well as aryl radical. So this is the first step in this reaction, where two aryl iodide separated by another aryl group through a double bond under photolytic condition undergo homolysis to give a I dot and aryl radical. This aryl radical undergo very nicely set for a radical cyclization to the adjacent aryl group which is present over here, and it can undergo this to give a this will add to this, and then it becomes radical here, and then this will so you can see it is going to give a cyclized product, and now two benzene rings are merge together or combine together through through the generation of aryl radical through homolysis of aryl halide, and then this once again dihydro derivative once again aromatizes to give with the loss of H dot from here, and which will combine with I dot to give HI. So this is, you can see, it is a nicely phenanthrene derivative, phenanthrene derivative is formed through a simple homolysis of aryl halide such as aryl iodide, which involves homolytic cleavage of the aryl iodide bond to give I radical, and then aryl radical, which nicely set for a cyclization to give dihydro derivative, which once again aromatizes to give phenyl. So this is a very interesting reaction where you're starting with a two phenyl group separated by a alkene group, can once again under photolytic condition can combine to give a polynuclear aromatic hydrocarbon as such as the phenanthrene derivative. Is another example here where we have a aryl halide, especially aryl bromide, and with some other functionalities such as this one and other. So we have another halide group with the exocyclic double bond. So under photolytic condition, this will similarly undergo homolysis to give a bromide radical as well as aryl radical. So this is the initial step which is generated on the influence of light. The aryl radical as well as halide radical, which is formed under photolytic condition through homolysis, and then this aryl radical is nicely set for the reaction with the exocyclic double bond, which is present in the other part of the moiety, which is connected through a ethylene group, and then this will add to this double bond to give a radical here, and then this once again generates get rid of the radical by loss of an hydrogen atom in the form of HBr to give a double bond. So you can see here we are starting with the two linkages. One aryl halide connected with a CH2, another functionality, but through a simple photolytic method which involves homolysis of the aryl hydride bond to generate a diradical speech, aryl radical as well as halide radical, which is can once again initiate the cyclization to give a 1, 2, 3, 4 tetracyclic ring system, where we have a 6-membered, a 7-membered, and then there's 1, 2, 3, 4, 5, and 6-membered. 2 benzene rings are joined together through this. So this is very interesting rearrangement of aryl halides through the under photolytic condition through homolysis cleavage, where we are synthesizing a polycyclic ring system through a simple radical cyclization of a nicely substituted functionality which is present adjacent to the aryl radical, which is generated on the hydrolysis of aryl halide. So these are two examples related to the aryl halides, where which can undergo homolytic cleavage through alpha bond cleavage to generate halogen atom and aryl radical, which subsequently cyclizes in a nice manner to give a synthetically extremely important compound, which we can see over here. Now another important aspect of this, the generation of carbocation, generation of carbonium ion on bridgehead carbon or a vinyl carbon. So for example, we have a generation of a carbocation on this bridgehead carbon, as well as the generation of a carbocation on the olefinic vinyl. Vinyl carbon is very difficult through the solvolysis of hydride, and but it can very well can generate through photolysis of corresponding bromide and halide. So in next few examples, what we would like to see over here is the generation of a carbocation on the bridgehead carbon, as well as the carbocation on a vinylic carbon, which is very difficult to produce through solvolysis of halides, but through photolysis photolysis of corresponding bromide and halide, which is possible to generate these two carbocation, which can further react with methanol to give the methanol added product. So here is an example. Here this is a bicyclic ring system. There is a presence of an halogen where X could be bromide or iodide under photolytic condition, may undergo homolysis of a to give a X halogen radical, as well as the carbon center radial on bridgehead carbon, and this bridgehead radical through electron transfer forms carbocation on bridgehead carbon, which on reaction with methanol gives methanol added product. So this is which is very difficult through any other catalytic method. Is possible to do it through photochemical method. So we can see that some of the very interesting products which could be obtained through photochemical methods, which was very difficult via any other means. So and then this can also this bridgehead radical may also abstract an hydrogen atom from the solvent to give the addition of an hydrogen on the bridgehead carbon, and of course alkyl radical which can combine in X dot to give Rx. So we can see here the normal through a generation of a carbocation through a normal solvolysis of an halide from a catalytic method is difficult, but it is possible through a photochemical method where the homolysis of the carbon halogen bond takes place to give X radical and a carbon radical, which through an electron transfer generate a carbocation on bridgehead carbon, which on reaction with methanol gives methanol added product on bridgehead carbon, or it can also abstract a hydrogen atom to give this hydrogen added product on the bridgehead carbon. There is another example here where the vinyl halide and then, as mentioned, the generation of a vinyl halide, the generation of a carbocation on vinylic carbon is difficult through normal solvolysis method, but under photolytic condition, it can here again X could be bromide or iodide, undergo homolysis to give X dot and the vinyl radical, which through electron transfer can form a carbocation on vinyl carbon, which can add methanol to give the methanol added product. So these are two very exceptional examples where the reactions which were very difficult through catalytic method can be brought about photochemically method via simple homolysis of the carbon halogen bond to give halide radical as a carbon radical, which can this radical through electron transfer reaction can generate a carbocation, which on reaction with methanol can give methanol added product. So these are four different very special examples of the photochemical reaction where the nicely substituted design starting molecule where we have an aryl halide or as this one as well as 5 can under photolytic condition under homolysis to give the halide radical or radical, which can subsequently cyclize to give synthetically important compounds. Similarly as the carbocation which was generated on the bridgehead carbon as well as on vinyl carbon through solvolysis method can be achieved via the photolytic method to give these products. Now coming to the third name reaction, that is Hoffmann-Lofter-Freytag reaction. In this reaction, an organic reaction in which cyclic amine such as pyrrolidine or piperidine is mainly the secondary amine or a primary amine as well, is generated by thermal or photochemical. So this reaction can be brought about both thermal as well as photochemical uh, thermal decomposition of N-halogenated amine to give in the presence of a strong acid. So the reaction involves the which cyclic amines such as pyrrolidine or piperidine on thermal or photochemical reaction. N-halogenated amine decomposition in the presence of a strong. So decomposes in the presence of a strong acid. The reaction proceeds via an intramolecular hydrogen atom transfer to the corresponding nitrogen radical, and this is an example of a remote intramolecular free radical carbon hydrogen functionality. So this reaction can be well understood by taking example as shown over here. So this is a nitrogen halogenated amine is an open chain system. You have an alpha, beta, gamma and delta. So 1, 2, 3, 4 carbon is important in order to generate a more stable cyclic system. So N-halogenated amine such as like this, where there is a presence of an 1, 2, 3, 4 carbon system with their R1 and R2 group. This is under photolytic condition, under photolytic as well as thermal condition, or any radical initiator can undergo the homolysis, yeah. First, to give this is a starting material, and leads to this the cyclic amine. The N-halogenated open chain amine can lead to, under thermal or photochemical, can lead to the formation of a cyclic amine. So overall reaction of this Hoffman Loeffler Freytag reaction can be represented as a reaction where N-halogenated amine open chain N-halogenated amine under thermal condition or photochemical condition in the presence of a strong strong acid can generate a cyclic amine. This is a highly generalized reaction where R1 and R2 can be R1 can be an alkyl group, or it could be H. R2 can be an alkyl group or acyl group, or it can be H. X, which is connected to nitrogen, can be chloro, bromo and iodine. So highly generalized reaction where N-halogenated amine open chain, where there is a possibility of 1, 2, 3, 4 carbon system connected to the amine, which may lead to the 5-membered stable cyclic system. So the synthesis preparation of a cyclic amine from an open chain N-halogenated amine is referred as the Hoffman Loeffler Freytag reaction. This has a lot of synthetic importance, because where the highly in a very synthetically nicely designed starting material, it is possible to construct the 5-membered nitrogen containing heterocyclic ring system. So the mechanism of this reaction can be represented as this is N-halogenated amine under acidic condition can get protonated to give N-protonated N-halogenated amine. This under photolytic condition undergo homolysis to give X dot and the nitrogen radical. This nitrogen radical can abstract a hydrogen atom from 1, 2, alpha, beta, gamma and delta carbon to give a carbon center radical, and then this this radical once again gets protonated. It will lose a proton to give the n n, and now the carbon center radical can combine with x dot, which is generated. Halide radical can combine to give carbon substituted. The halogen substituted carbon, and this lone pair of nitrogen can add to this to give the cyclized product, and then the positive charge on nitrogen can be compensated through the loss of a proton from here to give ultimately leading in the form of a minus HX. So this is the overall mechanism involved in this named reaction, where N halogenated amine open chain alpha, beta, gamma and delta, where there is a presence of a 1, 2, 3, 4 carbon system, a highly generalized reaction. We can have an R1, R2 could be an alkyl group, or R1 could be an alkyl group, aryl group, or could be H. This could be alkyl, aryl or H, or this could be alkyl or acyl or H. And then first step is the protonation in the presence of a strong acid to give a protonated amine, and this under photolytic condition can go homolysis to give X halide radical, and this halide radical, the N radical which is generated can abstract an hydrogen atom from 1, 2, 3, 4 carbon system to give a carbon center radical. This carbon center radical can combine with a halide radical which is generated over here to give halogen added carbon, and then this the lone pair of nitrogen can once again initiate the cyclization to give this which will lose a proton to give the neutral cyclic amine. So overall reaction, an open chain amine, N halogenated open chain amine can lead to cyclic amine. It has a lot of synthetically important because it can be utilized for the synthesis of a bicyclic, tricyclic system, and the application of this reaction can be looked into this if we have a properly substituted N halogenated amine can under photolytic condition or thermal condition or reaction can give a cyclized product. So we can see it's a very interesting from synthetic point of view. Same as this one, if we have a it can substitute H by halogen. It can under photolytic condition can undergo homolysis to give N dot, and this N dot can N radical can abstract in hydrogen from this adjacent piperidine ring to give a carbon center radical, and which will once again this will combine with the X the X dot halogen radical which is generated here, and then this nitrogen can initiate the cyclization. So we can see that the open chain with the 2 piperidine ring can lead to a tricyclic ring system. So it is a very important reaction, this named reaction, where properly substituted N halogenated can lead to the this is another interesting example where you have an amine with, of course, with a phosphorus phosphorus substitute derivative, which could be due to the leaving group. Here we have a methyl group here. So this can once again H can be substituted by an halogen, and then this can undergo under photolytic condition can undergo homolysis, can generate a N dot, can abstract an hydrogen atom from this, and then this will once again initiate the cyclization to give a cyclic system, so open chain system. So you can see the application of this named reaction, what we call is a Hoffman-Loeffler-Freytag reaction, is really important, because from open chain we are synthesizing a cyclic amines, and it has you can see the synthetically importance of this reaction, because from a nicely well substituted starting material can lead to cyclize the cyclized monocyclic, bicyclic, tricyclic, and tetracyclic ring system via photolysis of a N-prop substituted halides. Thank you very much.